So last time, right, we talked about this idea called modulation and demodulation. Let me scroll all the way up here, right? Where is it? No, it's just blank, right? And that's how you're able to change a low frequency signal and send it, in some noisy area where you have high frequency. You're able to send it with high frequency and therefore reduce the amount of noise that will interfere with your signal. And there's one more thing I forgot to mention on Wednesday, is that the size of the antenna, right? If you were receiving a radio signal, okay, depends on what is the wavelength of the signal you're trying to receive. Okay, so this is something we talked about. Those of you who had General Physics 2 when we did electromagnetic waves talked about this a little bit, just seen this picture before, where, right, electromagnetic waves, oops, let's do black, right? Let's say I have this is, let's just plot it in terms of space. Okay, maybe this is an E field as a function of space, so this will be some sine and cosine wave, right? And then of course the magnetic field comes out, perpendicular to it. Yes, this looks familiar a little bit, right? Okay, so this electric field, right, has some wavelength, right? Peak to peak, you get to figure out the wavelength, right? In order for an antenna to pick up the signal, okay, what the one side of the antenna has to do is be at the peak of the electric field, the other side to be in the trough of the electric field. That allows you to differentiate, basically maximize the amount of electric fieldness, right? You're basically going from peak to trough, or in these devices call it peak to peak value, right? Because let's say if you're only using one, let's say this antenna is like half the length, right? So all it will be able to pick up is this part to this part, right? Which will have a smaller amplitude, right? So you're not able to measure the entire amplitude of the electric field, unless, right, your antenna is at least the wavelength of that electromagnetic wave divided by 2. And hopefully this little picture makes sense, right? Because from here to here is half a wavelength, right? It's going from here to here, right? That's half a wavelength. You guys see that? Okay. So if you want to pick up a signal, right, you want to measure at the same time the peak and the trough of that wave, right? That way you can actually measure it. If you have a shorter device, then you will not pick up the entire signal. Okay. You can still see it, but it will be a little bit weaker. Okay. So so I'm just going to do some examples. So those of you might have seen this before, right? Let's say I have a 100 hertz electromagnetic wave. How long do you think the antenna is supposed to be? Anyone want to venture a guess? I'm just going to do the calculation while you guys take a guess. Just guess. You don't have to calculate. I'm doing the calculation. Anyone wants to guess? Three times 10 to the 6. No one guessed it? 3 times 10 to the 6 meters? Okay, so 3 times 10 to the 6 meters, that's about 3,000 kilometers. Okay, well, technically you don't need this long, right? You need just that wavelength divided by 2. So you need antenna about 1,500 kilometers long. So this is from here to like Denver. That's how long your antenna has to be in order for you to pick up a signal using electromagnetic waves that is 100 hertz, right? So you probably don't have a lot of those antennas, right? In fact, I don't think there are any. Okay, let's just do a few more examples. So if the signal is 100 megahertz instead, so I put, right, 100 million down on the bottom here instead. times 10 to the 6, 1 over second, right? Most of this cancel out, so this will be 3 meters, okay? So the antenna length, right, will be about 1.5 meters, okay? Okay. Where have you guys seen 1.5 meter long antennas? About a meter long. Where? Car antennas, right? There, and there's no and what is the frequency of like FM radio on your car? About 100 megahertz. That's why they make it that long. Okay. Let's repeat this for 2 gigahertz just to be a little annoying and get you guys to. I'm sorry. So you can, it's basically, I'm just showing you this pictorially. You can do the calculation yourself if you want, right? So as the electromagnetic wave passes through your antenna, right, you want one side of the antenna, in order for you to, have this oscillation of, oh, you get the plus charge on this side and negative charge on the other side, right? What you want to do is you want the peak of the electromagnetic wave on one side of the antenna and the trough of the wave on the other side, right? Because what happens if you cut this in half, right, you're only measuring this part and you're losing out that end point, right? So to basically maximize the amplitude or the amount of signal you will pick up, you want at least for it to be half the wavelength. Okay? Is that why the function generator is the way that it is? It's always lambda over 2. Function generator lambda over. Whenever we're setting it, how we start with a 5 volts amplitude. That's the amplitude and peak to peak. That's a different. It's just that's just a convention thing where when you set the amplitude, right? When the function generator says amplitude, you're actually setting this value, right? This is V, peak to peak, right? The real amplitude in physics is this, right? Let's say this amplitude is 5 volts, right? You're setting the peak to peak value to 10 volts in order to get that amplitude of 5. Okay, that's just a little silliness with the function generator design. Okay, okay. So 2 gigahertz. Okay. Anyone wants to venture a guess how long of an antenna I should get to get a 2 gigahertz signal? Something about the size of what around here? What picks up 2 gigahertz signal for around here? Phone. Yeah. So something on the size of the phone. And let's see if that's true. Okay. So 2 times 10 to the 9, 1 over a second. So that's the frequency, right? Most of this cancel out to power 1. So it's 1.5 times 10 to the negative 1 in meters. In other words, 0.15 meters. Okay. So the length you want is about 7.5 centimeters, right? Because you move this over, right? It turns it into centimeters. So guess what's about 7.5 centimeters in my pocket, right? There's a reason why the phones are this size, right? Besides your screen, people. But that's the secondary thing, right? Where, if they can make phone, like half as big and still have the same signal strength, they would do it, right? Because there's a market for that, right? So, so there's a reason why things are the size they are, right? And all of this information, all these frequencies I'm talking about, you can use a carrier signal even though a carrier frequency of 2 gigahertz, even if I'm sending information only at 100 hertz, right? And this is the idea of modulation, right? Last time, okay, what we were able to do, okay, is we multiply your signal, right, with some omega s, right? It will be, 6.28 times 100 hertz, right? And you multiply that by some function, that's the carrier frequency. So maybe it's 1 megahertz, right, or 100 megahertz, depending on which device you're sending it to, okay? So this is going to be a high number, and this is a low number, low as in something that you want to send, right? When you multiply these two things together, you get this blobby thing, okay? You get this, in general physics 1, we call this the interference pattern, right? But this is actually what's happening when you multiply these two functions together, okay? And we talked quite a bit about how a multiplication actually happened, right? How does electronics multiply? What basic device is needed? Anyone remember from last time? You need an op amp, but what's the thing that allows you to multiply? Diode, right? Diode has this behavior where it's an exponential growth in current as a function of voltage, right? But then if you invert that, right, if you have current as, voltage as a function of current, you end up with a log function, right? And oops, I think a log function actually goes like this. Okay, a log function, when you take the magic of log function is that when you have, let's say natural log of some function A, and you add it to some log function of function B, you end up with the natural log of FA times FB, right? Basically, it converts additions into multiplication, right? And that's the magic of diodes. Okay. Anyway, so these little diodes allows you to do this multiplication, right, in electronics. But we can just keep doing math on it, and then one of the trig identity is that when you multiply two cosine functions together, you actually get sum of two cosines, but then their frequencies basically changes from minus to plus. Okay? Right? And why is this useful? Because, right, the carrier frequency is going to be a large number, let's say like 100,000 or something like that, and your signal is just 100, right? 100,000 minus 100 is basically 100,000 still. 100,000 plus 100 is about 100,000 still. So this entire signal, the modulated signal, is high frequency, okay? So now you can send it over an antenna, right? That's not, from here to Denver, right? And still be able to transmit that information. And also you get away from all the atmospheric noise and all the man-made noise that's all around us in order for us to send those signal without having to deal with interference from them, okay? Okay, so everyone's okay with this, how just by multiplying these two functions together, right, allows you to do this? Make sense? Maybe? You get to do it in the lab, so you'll see it. All right, okay. So, so how do we demodulate the signal, right? So this is called the modulation. Oops, modulation, right? That's the mod, right? Demodulation is the dem, and you combine them together, you make a little modem, right? Okay, so the way you demodulate the signal, you do the same thing, which is interesting. You take whatever this is, right? That's what your input is, and you just multiply it by another function of cosine, right? You just, okay? But this has to be special because this has to be exactly the same frequency that you modulated the signal with, okay? Otherwise, it doesn't work, okay? Because otherwise you will just get beat frequencies, okay? Okay, right. And this is actually one of the first ways that when people started, sending information over radio wave in the 20s, this is actually one of the ways to keep your signal secret, is by just keeping that frequency secret, where no one knows exactly what it is. So you actually don't. It's really hard to detect the signal unless you know exactly what the carrier frequency is. Okay, but let's go through the math, right? So if I multiply this, right? Well, the original modulated signal is this, right? Remember it was just me, multiplying to these two signals to get the signal and the carrier together, right? Now I'm just going to undo that, okay? Okay, right? So instead of grouping these guys together, what I'm going to say is that, well, I'm going to group these guys together and see what happens, right? I'm just doing math, right? Okay? And interestingly, math represents reality a lot of times, okay? So what happened is that here you have your original signal. Oops, there's actually an AS here, AC here, sorry, that's missing, okay? Yeah. So the amplitude of the carrier, okay? Okay. What happened is that you have this cosine multiplied by itself. Well, when you multiply a function by itself, that's just the square of it, right? when you have a square of cosine function, there's yet another trig identity, cosine square of x is equal to 1/2 1 plus cosine 2 omega 2x. Okay, 2x, just x. Okay, all right, that's another trig identity that either can memorize or can just figure it out. Okay, so what I can do is then replace this with here, right? Right. Now what I'm going to do is I'm going to multiply this signal function, right? This f is not frequency, it's the function of the signal, right? Into each of these terms, right? Then what you'll see is you get a low frequency term, right? That is exactly the same frequency of omega s, okay? And then, yeah.
Right at the very beginning, whenever you multiply like the carrying frequency again, are you doing it without the AC?
With the AC. The AC is always around, unfortunately. Yeah, I just forgot it.
So then if that's the case, how come it's not AC squared?
AC. So I pulled this out, okay? Oh yeah, okay. If I pull this, yeah, so there's an AC here also. Well, the thing is that the amplitude could be different between the two carriers. Yeah, you're right. So there's a square here. Okay, square everywhere. Okay, yeah, thanks. Because the amplitude doesn't actually matter that much because you can end up amplifying it anyway. So, okay. All right. So this part, right, has a frequency of 2 omega c, right? So this is our high frequency piece, right? Okay, right? So you have some low frequency stuff you want to keep. You have some high frequency stuff you want to throw away. So what do you do? Anyone? Yeah, you just do it. You just pass it through a low pass filter. You filter out these high frequency, and then you end up with your signal, which is the demodulated signal. Okay, and Shane's right. It's actually proportional to that squared. Okay, so let's say the amplitude is 1, right? Of all these things, right? Then you basically have a factor of 1/2, right? And what you end up usually doing, since you're sending the signal over some long distance usually, even though you're not doing it in this class, okay, you'll lose a lot of the amplitude anyway. Okay, so maybe you'll lose a factor of 1,000 amplitude, but then you can amplify it using the stuff you guys already know how to build, which is just op-amp amplifiers, right? Okay, so that's why op-amps are essential, right, in order for you to receive these signals. Okay, so as I noted, any questions before I move on to some drawback of full modulations? Okay, so as I noted in the beginning, this requires both sides of the device, right, to have requires both sides. Okay, well, it requires both sides of the device to have something that multiplies things together, right? Which is going to be a special chips that you're going to use to multiply these things together, and also requires that the carrier frequency be shared, right, between the two sides, right? If I don't have the carrier frequency, I cannot demodulate the signal at all, right? I can guess what it is, but it will take me a long time. Okay, all right. And you can also change the carrier frequency as a function of time. So like on Monday you use one frequency, Tuesday you use a different frequency or something like that, right? And then keep people guessing. Okay. Okay. And since the carrier waves are usually highly amplified, right? Even a small difference in the transmitter frequency, transmitter carrier frequency and the receiver carrier frequency, that's going to create a large difference. So even if you're slightly off in the frequency, you're just going to get garbled. Okay, which is something that that needs to be taken care of, right? In order for you to have the same exact frequency between the two sides, what communication devices actually do is they use something called a lock-in mechanism. Okay, and this is just a little lock-in board where you have your signal, which is f sub s. You just write it down, right? This is the FOS going in. There's also this sync signal. This is just a synchronization thing. But what's important for our discussion is that your modulated signal is sent along with your regular signal. So now you actually have two lines, right? One's to send the information, right? The other line to send just the modulation frequencies, okay? And this is actually what you'll see in a lot of your cable modems, where inside the cable modem, there's actually a divide where it actually has the carrier frequency and the information being sent at the same time, okay? And that way, whatever you're demodulating will be exactly what the frequency that they modulate it with in order to send that across, okay? In fact, so this is gonna, I don't know if you guys ever hear these anymore, okay? If you still use fax machines, you might see them. Is it trying to, what is it trying to do? I'm trying to click on this link, which is not easy. Come on, don't run around. Link, open. Hopefully I'm not just opening .com. Oh yeah, it's open already. Never mind. That's why it's so slow, because I'm trying to open like 3 copies of it. Oh, I need to connect the speaker anyway. Okay. Play this, but not into my ear. Do you guys ever hear that anymore? Maybe it's just Has anyone ever actually used modem ever in their life? Right. The reason you're hearing this is because the modem, right, used to work over the telephone line, and the telephone line is only designed to carry sound frequency, right? So that's why, right, when your modem connects with each other, what they're doing is they're negotiating. They basically say, oh, I want to use this, the sender will say, okay, this is the carrier frequency I want to use. And say, oh, can you use that? And say, well, no, I can't use that. And then your modem will send back to, okay, this is the carrier frequency I want to use. They're basically negotiating which frequency to use in order to figure out what their carrier frequency is. And on telephone type of modem, you can actually hear it because the frequency is low enough so that you can hear it with our ears. Okay? The same thing is happening in your DSL modem and your cable modem, but those are running at like, hundreds of megahertz. That's why you can't hear it. Okay? So that's the difference between them. So let's go back to the lecture. Okay? Okay? So, and each of these little lock-in device and then a little multiplier on your end, right? Those typically cost about $50, and that's probably why your modem costs about $50. Okay, that's just the basic cost of it. Okay. So there is a cheaper way to do this with a little bit. You pay a little bit in basically the transmission rate, so you wouldn't use this to watch, I don't know, Lord of the Rings or something like that. But you could, send information like, someone just talking, which is very little information, okay, such as an AM, FM radio, or some music, using this idea called the partial modulation. Okay, the advantage of partial modulation is that you do not need a lock-in on the receiver, and you also don't need a multiplier on your receiver. Okay, so you can actually make a receiver at a cost about $1. Okay, and which is the reason why they do this. Okay, so in order to do partial modulation, what you need to do is you need to set an offset of your signal, Okay, notice that this signal is always positive, right? The previous signal could be positive or negative, right? So instead of oscillating around 0, it's oscillating about 1 volt. Okay, it doesn't have to be 1 volt, but you never want the signal to go negative. Okay, so that's the difference. Okay, when you multiply this with the carrier wave is still going plus or minus. Okay, instead of, oops, let me zoom out a little bit. Instead of getting twice, remember last time we had like 2 lobes, so it basically doubles the frequency, right? In partial modulation, you don't get that effect. You basically have just the same frequency in your number of lobes per second. Okay, so you don't the signal never goes negative, so therefore you don't have this flip upside down, upside down, upside down all the time. Okay, so once you know whoever you're sending this information to, this modulated signal to, right? This line here, right, is basically what your signal is, right? Because it's the same frequency, right? And it's also correlated with the same amplitude, okay? Because when you're sending this information, you're either carrying the information by telling people how big the signal is, right, by amplitude, or by what frequency. There's also a way to send it through phase modulation, but we're not going to deal with that in that class because it's hard to show. But, right, so whatever this input amplitude is, right, it's going to be proportional to this one, right? Whatever the frequency of the signal is, it's going to be proportional to this one, right? So therefore, you're actually sending this entire wave over this carrier frequency by modulating it, and by just picking out, right, this low frequency part, right, you will get the same information back. Okay, go down, okay. So in order to do a partial modulation, it's much simpler, okay? So on the transmission side, remember that you basically need to make sure, right, whatever your signal is, I'm just going to do a schematic, a little drawing of it, right? This is the information you're trying to send, f sub s, right, as a function of time, right? You shift it up so that it's always positive, right? Okay, right, okay, you shift it up. Then you take that, you multiply that by your carrier wave, right? Which is still, you know, this thing, right? Then your, whatever your modulated signal is, looks like this up here, okay? Then after you receive it, right, then you send this out into the airwave. On the receiver side, right, what you're gonna see initially, right, is this, right? These little lobes. I know I'm not drawing the one that's good, right? Right. So if you want this piece of information, right, once again, you just do a low pass filter on it, right? So you want to remove all this wiggleness, right, and only preserve this part, right? This is a low frequency signal, right, being carried through a modulated signal like this, okay? So what you want to do is you pass it through a, let's do an active low pass filter. Do you guys remember how to build one like that? Maybe with an inverting op amp. Anyone remember how to do that? Right. You got a little capacitor here. I think it is. I think it is right. RF. R. Oops. That's not an R. That's a capacitor, right? Right. Is that right? At low frequency, you basically have, this is a short, right? Then you get this as a application. Okay. At high frequency, this becomes, sorry, at low frequency, this is basically an open, right? A capacitor is open. Basically, pretend if DC, then the capacitor, no current passes through a capacitor, right? At high frequency, this becomes a short, and then you get no gain. Yeah, right. Okay. You guys believe me? No? Maybe. You can just figure it out yourself, right? because the op amps are so, you just need to know the two little rules, and you can actually figure out everything about it, right? Okay, so so that's how you do partial modulation, where you have to make sure your signal is shifted up so it's always positive, so you don't have this up and down, right? Where you're multiplying a positive to a negative twice as fast, okay? And then you just send that over, you multiply it by the carrier, this F sub C, right? And then you send that over the air, and then you do a low pass filter on the other end, okay? There's more technicalities in that, like how do you build the antenna, how do you detect the signal, all that stuff, and we're gonna see this in the lab, okay? In fact, if you want, you can build an AM radio, right? So A1 is an antenna, so this will probably be something on the order a couple of meters long in order for you to pick up the AM signal, okay? And then you connect this through a capacitor. This is just so that you block the any DC bias, okay? It's not, you know, it's an engineering thing, not a physics thing, let's say, okay? And you have a inductor and a capacitor here that you can tune, right? And by changing the C value, right, what are you changing here in this little parallel LC circuit? What are you changing? The resonant frequency, right, which is 1 over square root of 2 pi LC, right? So this is the part you can adjust. This is something you just install, and you're stuck with that, right? You don't want a tunable inductor because that's going to be super expensive and not reliable, okay? And then you put this through a diode, okay? The reason you put this through a diode is because, right, you don't want the negative part, right? You only want the positive part, right? That allows you to pick out the positive part, okay? And then there's an additional capacitor here just in case there's some, current that runs to the ground. So these are more engineering capacitors. And then you put it in a speaker, and then you have sound. Typically, you actually probably have to amplify this, unless you have like an array of like, 1,000 line of antennas, right? You're not going to pick up a signal that's strong enough to drive a speaker, okay? So you probably have to put some amplifier in here, okay? But once the signal is there, you can amplify that signal and listen to whatever music you want, right? Or, right, some of you guys, right, actually start picking out satellite communication frequencies. So like all the communication around the globe is all open in the air, right? The thing you need is basically figure out what their carrier frequency is, right? You can demodulate it, but sometimes it may be encoded, okay? But that's another problem, okay? So, but you can definitely, just with a piece of metal, pick up any signal you want, and the carrier frequency sets the length of that piece of metal that you have to make, okay? All right. Yeah, so what you guys are going to do in the lab is you're going to be sending your signal across the breadboard, but once you have the idea how to send a signal over 6 inches, you can send it, 6,000 miles away, right? It just requires amplifications and good cables or open air, right? Something that allows you to transmit, right? So that's more of an engineering problem, not a physics problem. Okay, and this information is encoded by amplitude modulation, as I mentioned, right? If you increase and decrease the amplitude of your signal, that's telling, whoever's on the other side, right? Oh, I'm increasing and decreasing the amplitude, right? Or you can even go digital. You can actually see it in the video I'm going to show you. You can either send 0 or not, or 5 volts, right? Then that allows you to encode information by just sending ones and zeros, right? The other ones you can do is by changing the frequency. By changing the frequency, you're basically making the wavelength longer and shorter, right? That also encode information, okay? There's the other one called phase modulation, where you're just shifting it around. It's really hard to demonstrate in the class with our oscilloscopes, but you can see that by just changing the phase, you will get a slightly different signal, okay? So there's 3 things, right? Because, this comes from this, basically, right? So a signal has some amplitude, it has some frequency, but it can also have some phase, right? Right. Those are the 3 pieces of information that can be encoded into a signal. Okay. All right, so I'm going to play this little video because it does the animation a lot better than I can. Um, and it does a lot of digital modulation also that we don't actually really cover in this class, but it's good to just see it. Hopefully the video plays. It's a pretty old video, so it's going to look like early 2000s.
Modulation is one of the most frequently used technical words in communications technology. One good example is that of your FM radio, where FM stands for frequency modulation. In this video, we are going to learn the basics of modulation techniques and see how they are applied in modern cellular and communications technology. Frequency and wavelength of a wave are inversely connected. Humans have the capability to hear sound frequency from 20 Hz to 20 kHz, but if a radio tower transmits electromagnetic waves of the same frequency, the size of the antennas required will be really high. In the antenna video we have already seen that the size of the antenna is proportional to the wavelength. If we had transmitted the electromagnetic wave in the same frequency of sound, the antenna size required would have been in the range of kilometers.
How come I got a different number?
This is why we need modulation. Before the electromagnetic waves are transmitted, they should be modulated to a high-frequency signal. We can understand the way we modulate the signals with a simple analogy. Try throwing a piece of paper. It won't go far. Now tie it to a stone and throw it again. The second method is obviously more efficient than the first one. This is exactly how we do modulation. In place of a stone, modulation uses a high-frequency signal known as a carrier signal. As we know, any signal has three basic properties: amplitude, frequency, and phase. In the modulation process, one of the properties of the carrier signal is varied in accordance with the message signal.
Okay, I
For
have to say something, I guess. I think that throwing stone thing is not really a good example. Like, one thing is that, right, you can think about it like the message is, what the letter you wrote, right? And the carrier signal as kind of like the envelope, right? Because if you just stick that piece of paper in the mail, right, and try to move it around, it's not protected, so it's going to get dirty, right? It's also not going to get very far because no one has any idea where it's supposed to go, right? Where an envelope, kind of protects the message and directs it in a place where you can send it, right? But I guess the throwing stone thing sort of works.
example, the frequency of the carrier signal is varied according to the amplitude of the message signal. This technique is known as frequency modulation. Please note that the frequency of a carrier signal is always high, which means the modulated signal is also of high frequency and energy. The value of the original signal can be easily retrieved from the frequency of the modulated signal.
Right. See, even though this is high frequency, it still has.
In the same way, we can also achieve amplitude modulation. Here, the amplitude of the carrier signal is varied based on the value of the message signal. The modulation techniques we have discussed so far have all been analog types. However, they are already obsolete. Analog modulation is susceptible to noise, which degrades the quality of signals. And moreover, in today's electronic instruments, all operations are carried out in digital form, where the digital signals are either a 1 or a 0. So, let's discuss the digital modulation techniques that are currently used. More specifically, let's see how the digital bit flow is converted to an electromagnetic wave. The first digital technique is amplitude shift keying. Here, based on the digital pulses, the amplitude of the carrier signal is adjusted. High amplitude relates to 1 and low amplitude relates to 0. The next technique is called frequency shift keying. Here, based on the value of digital pulses, the frequency of the carrier signal is adjusted. In this case, high frequency relates to 1 and low frequency relates to 0. The third technique is phase shift keying. Here, the phase of the carrier signal is changed by 180 degrees when the digital pulse moves from 1 to 0 or 0 to 1. Telecommunications technology is all about increasing data transfer speed and efficiency. But if you use any of the digital modulation techniques explained previously, you wouldn't get a high data transfer speed. However, there is a technique in physics which, if you use it, means you can practically send up to 6 bits of information as a single electromagnetic wave. This technique is known as quadrature amplitude modulation. To understand QAM in an easy way, let's take two analog signals. The beauty of QAM is that you can modulate these two different signals as a single signal and then transmit it. Then at the receiver end, you will be able to separate out the original signals, thereby saving bandwidth.
So now you send
Let's see how this modulation is done. In QAM, the first signal is amplitude modulated using a carrier wave as shown. The second signal is also amplitude modulated with a carrier wave of the same frequency and amplitude, but after giving the carrier signal a 90-degree phase shift. Now, these two modulated signals are mixed together and form a single signal. We call it a multiplexed signal. The interesting thing is that on the receiver side, we can easily separate out the original signals from the multiplexed signal. In the case of digital QAM, a similar approach is used. Here, instead of analog signals, different combinations of bits are added together to produce a multiplexed signal. Let's see how a 16 QAM works. If you are familiar with digital technology, you know that any form of data is just a collection of ones and zeros. In 16 QAM, we can pack 4 bits together and send it as a single electromagnetic wave. Based on the values of the 4 bits, this output will have different phase angles and amplitude. This means the phase angle and amplitude of the multiplexed signal can completely represent 4 bits of data. In 16 QAM,
I pause at exactly the reverse time.
Such 16-bit values.
Okay, so it's be a little clear, like you would think this little wave is the same as this little wave. They are shifted in phase. Okay, that's the difference between them. Okay.
Can be represented by adjusting the phase and amplitude of the multiplexed signal,
Modulation and phase modulation.
and this single multiplexed signal is then used for the transmission. You can see how the different amplitude and phase electromagnetic signals represent various 4 bits of data. Using a similar technique to that used in analog modulation, here the amplitude modulated signals are also mixed together, and finally, a single output is produced. As we have seen in this modulation, 2 carrier signals that are out of phase by 90 degrees are used. Hence the word quadrature is used to refer to this technique.
It's 1/4 of a circle, right?
If, instead of QAM, we had used a normal modulation technique to send bits of data, we would have used 4 electromagnetic signals. Thus, 16 QAM increases the data transfer speed by 4 times. Scientists have even achieved 64 QAM, which is used in 4G communications. 64 QAM uses 6 bits of data at a time, thus making the data transfer speed 6 times faster compared to a normal modulation technique. The modulation techniques are not restricted to only cellular communication and FM radio, but also have applications in television broadcasting, Wi-Fi, optical fiber.
I think that's enough. Let's not advertise DirecTV. I don't even know this company still exists or not. Do they? They still exist. Okay, so that's the modulation. So hopefully you'll get to do a little bit of this